welcome back. Eigenvalue and eigenvector. That's our last topic to look at under linear algebra. Alright, so now eigenvalue and eigenvector. Good. So a number lambda is called the eigenvalue. So the lambda is what we call the eigenvalue of the square what matrix. That means that the matrix that will be given to you should be what a square matrix, whether 2 by 2 or 3 by 3 or 4 by 4. Alright. If there exists a non-zero vector that such that alright. Now if lambda is an eigenvalue of A, then any vector that satisfies is called an eigenvector of A associated with what? Lambda. Don't worry, I will not even use this to get you the concepts. I'm bringing this straight away from the characteristics equation. So now, when you are asked to find the eigenvalue, we have the characteristics equation for doing that. And finding the eigenvector, we have the characteristics equation for what? Doing that. So, looking at this question, find the eigenvalue of this. So, you first start with your characteristic equation that says the determinant of A minus AS times the identity matrix. So, now this is derived from this. I don't want to go there, but that's where it was derived from. The A is the matrix, the lambda is the eigenvalue, the I is the identity of that matrix given you. So this is 2 by 2 matrix, so we write the identity of it. Alright. Let's move on. So let's see how we find this eigenvalue. Alright, so you first write the matrix A. And the matrix A is 1, 2, 3, 2. Minus lambda of the identity what? Matrix, which is 1, 0, 0, 1. Good. Equal to 0. So that means that the whole whatever is here is what we are finding the determinant of. That's why we are having the depth there. Alright, so now the depth of 1, 2, 3, 2 minus, so when you multiply this through that, you are going to get lambda 0, 0 lambda. Alright. So after here, then repeat the depths. So here you are going to get something like, you subtract, this is subtraction, so the corresponding components, right? So 1 minus lambda, that is that. Then 2 minus 0 will be 2. Alright? So 3 minus 0 will be 3. So here will be 2 minus lambda. So that's what we are going to get. So we are now going to find the determinant of this. Me and you is aware is 1 minus lambda multiplying, so write it this way, multiplying 2 minus lambda minus 3 multiplying 2, right, equal to 0. And when you do that, you are going to get 2. Alright, so you are going to get 1 minus lambda, 2 minus lambda minus 6 is equal to 0. So this is going to give you a quadratic equation of lambda squared minus 3 lambda minus 4 is equal to what? 0. And then, because here is going to be lambda squared here. So multiply it by that by that, and that's what you're going to get. So lambda squared minus 3 lambda minus 4. And when you point your calculator, you get lambda to be equal to 4 and lambda is equal to negative 1. Therefore, this becomes the eigenvalue for this square what? Matrix. Alright, so you have to try on, I hope it's not difficult. Just write your matrix down, just like that, find the terminal so you are done. Alright, so you try on, find the eigenvalue of 4, 2, 3, 3. Alright, and you are going to get lambda to be equal to 6 and lambda is equal to 1. So, see you for the next question. Alright, welcome back. Now that we know how to find the eigenvalue, then we can now go and see how we can find eigenvector. Because it's the eigenvalue you use to find the eigenvector. So I told you to pause the video and try on this. I hope you did that. And you get lambda is equal to 6 and lambda is equal to 1. So now, let's go to our next question under that. So find the eigenvector of, now this square matrix, we are going to use it to find the eigenvector. Right? Good. So don't forget the formula I gave you in finding the eigenvalue. The eigenvector is different. The eigenvector is going to be A minus lambda times the identity matrix is equal to, no, then this one will come is equal to 0. So so we have to know it offhand. That's what we are going to use to find the eigenvector. Good. Now, from this question, we are not going, you have to go back in finding the eigenvalue. So we know it already that lambda is going to be 6 or lambda is going to be what? 1. Now, in finding the eigenvector, two cases come in. There are some times that your results is going to, you let's go to 2 and see what you are going to get. So now, from this eigenvalue that we are going to take it one by one, okay? So let's start. Alright, so from what we have there, A minus lambda I is equal to 0. So, the A here is a square matrix 4, 2, 3, 3 minus lambda and the square and identity will be 1, 0, 0, 1. Beautiful. Then this one is, if you repeat that one, is equal to what? 0. Good. So now let's move on. So with this, we are going to get 4, 2, 3, 3 minus lambda 0, 0 lambda is equal to 0. So with this, we are going to get 4 minus lambda 3, 2, 3 minus what? Lambda. Then you bring your and that's it. That's good. So when you reach this part, then you know that we have two possible values for what? The eigenvalue. So you start for lambda is equal to, let's start with the 6. Lambda is equal to 6. So do the substitution. So 4 minus 6, right? 3, 2, 3 minus 6. Then you bring this equal to what? 0. Okay, I'll tell you something about this. Don't worry, you bring it. So here you are going to get 2, 3, 2 negative 3, that is equal to 0. Alright, so when you get to this side, then this one we have here can be written as, so this one we have here can be written as negative 2, 3, 2, negative 3. Then here will be, let's say T1, T2, or we can see that, or S1, S2, then you have, and this can be 0, 0. Alright, so you know how to solve the system. There. So I don't need to worry. It's something that we know already. So here is going to be negative 2, 2, 3, negative 3. We get 0, 0 here. Good. Then we solve the system. So you can use reduced row echelon form. So that here we say that let's divide here by 2. Alright. But we have to negate it because here should be 1. That's why I have negated it here. And put it at new row 1. So when you do that, you are going to get 1, negative 1, negative 3, 3, negative 3, 0, 0. Then you come back to this. This should be 0, this should be 1. So what will you do? R2 minus 3R1. And put it in the new row 1. And put it at new row 2. You know how to do this already. So, because you multiply this by this and you subtract, it's going to be 0 for you. So you are going to get 1, negative 1, 0, 0, 0, 0. Alright? So that's what you are going to get for that. And when you rate this part, here is going to be so here, okay, so you can use, let's use S1, S2. So here 0 is equal to 0 is true, right? So we can get S1 minus S2 is equal to what? 0. Okay, so now, since we have here, that means that there is a lot of what? Solution. Alright, so after getting this, then you can see that S1 is going to be equal to what? S2. So if S1 is going to be equal to S2, therefore our solution is going to be TT. Why TT? Because we can see that there is infinitely many solution. So we have to assign a parametric form for it. That's why we used to be TT. Alright, so or this can be written as T11. Now, having this, because of the T there are many vectors. So here it is called vector space. So when you get TT like that, that means that it is called vector space. So that is what we call a vector space. Let's look at the other side. You can try on it for when lambda is equal to what? 1. I'll be back. Alright, so for lambda is equal to, I hope you have also tried it. For lambda is equal to 1, that's what you are going to get. Going by this is something that you know already. Using reduced row echelon form. So when you get to this side, then we can do what? Back substitution to get this. Alright? And since 0, we are having 0 here means that infinitely many solution. So you have to assign a parametric form for it, and that's that. So x2 will be equal to this, and since we are assigning a parametric form for x1, sorry, x1 will be equal to this, then we assign a parametric form for what? x2. So that means that x2, so that means that x2 will be equal to what? T. x2 will be equal to what? T. And when it happens like that, you are going to get this. So since we are not getting here to be tt, like what we have in at where lambda is equal to 6, we can say that this is a vector, eigenvector. This is an eigenvector. But where lambda is equal to 6 is the eigen space. Then, so there are sometimes you can be given a 3x3 to find the eigenvalue of that one matrix. So the same idea like that, you multiply this by that, and that's what you're going to get. But this is the case that you have to find the determinant of this. That's going to be something else. I hope you can see that. Alright, so when you find the determinant of this, you know yes, plus, minus, plus. Then you use that to go equate to 0, and you are going to get a cubic function. Alright, so when you solve it, you get lambda is equal to -2, 3, and 1. But let me give you some hints. There are some times that dealing with this becomes something complex for you. I'm going to give you a short technique for you to come out with your solution without going by that way out in finding the determinant. Okay, that's what I used, and I'll let you know it. Stay tuned. Alright, so when you're given a 3x3 matrix, it means you're going to get 3 solutions for lambda, and this is where the idea is coming from. Alright, so you have to understand the tri-A, the PMA, and the det A. The det A is clear. That is you finding the determinant of what? The 3x3, whether on your calculator or whatever. Alright, the tri-A means that the A11, the A22, the A33, that is the sum of the diagonal entries. The sum of the diagonal entries. So you sum them up, and that is what is going to form that. Alright. So you just write that value there. Then you come back to the PMA. That is the sum of all the minors of the main diagonals entries, called the principal minor of what? A. So you look for M1, M11, M22, M33. Then you sum them up, and that is what is going to give you this. This value. That value is going to give you that value. So how to find the minors? That one you know it already. So from the minors, you just sum all the minors of the main diagonals entries. That's it. Alright. And the last one is the det. That's the determinant of the whole matrix. So that's how you do it. You can go by this short method, or you go by finding the determinant of whatever you're going to get there. The rest is up to you. See you. Bye bye.